Hi everybody, in this video we are going to do a proof of the Pythagorean theorem, which is also sometimes called Pythagoras' theorem, because Pythagoras was a real person. And here is the theorem. In any right triangle, a squared plus b squared equals c squared, where a and b stand for the legs of the triangle, and c stands for the hypotenuse. So first of all, what do we mean when we say the legs of it? Well, first of all, what's a right triangle? A triangle is just a triangle that has a right angle in it, that is a 90-degree angle. Okay, so you can see that this triangle has a 90-degree angle in it. This is the angle right here, which is 90 degrees, and that is sometimes represented with a little square symbol. That means that this is a 90-degree angle over here. Okay, and what do we mean when we say the legs of the triangle? The legs of the triangle are the sides that are adjacent to the 90-degree angle. So in this triangle, the legs would be this side and this side. Okay, these are the lines which form this 90-degree angle over here. And the hypotenuse just means the side that is opposite from the 90-degree angle. So in this triangle, this over here, this side would be the hypotenuse, which you can see is opposite from the right angle. Okay, so we have here where a and b are the legs, and c is the hypotenuse, we have a squared plus b squared equals c squared. In other words, if I take the length of this side and square it, which means multiply it with itself, and I take the length of this side and square it, and then I add those results together, what I get, the number that I get would be the same as what I would get if I took the length of the hypotenuse and I squared it. And another way of saying that in words is that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Okay, so here are the squares of the legs. The sum of the squares of the legs means we add these two together, and that is equal to the square of the hypotenuse. All right, so what we're going to do for the rest of this video is we're going to actually prove the Pythagorean theorem. So what we have here is just an arbitrary right triangle. Okay, it doesn't have to, it works with any right triangle. It doesn't have to look exactly like this one with side lengths exactly like this. As long as we have a right angle in that triangle somewhere, then the theorem that we're going to prove right now applies to that triangle. Now, here's how, there are a number of ways of proving the Pythagorean theorem. Here's how I'm going to do it over here. I'm going to take this triangle and I'm going to make 3 copies of it. So now I have 4 copies altogether. And then I'm going to arrange these copies into a square. This is kind of fun to do, actually. A little bit tedious, but a little fun too. You can see we're going to get a nice sort of design at the end. Okay, move that in here. Okay. All right, that's pretty good. Okay, so all I did was I took this triangle, I made a few copies of it, and I arranged them in order to get a big square over here. So I'm going to call this square the outer square, and I'm going to call this square, you can see I got another square in here, I'm going to call that the inner square. Okay? And you know what, actually, before I go any further, I should probably label these. Really, I should have done that in the beginning. But, so let's just call this over here, this side length of the original triangle A, and we'll call this side length B, and we will call this side length C. Okay, so then after making those copies, then I have A's and B's and C's all over the place. Remember, all of these triangles are congruent to each other. I didn't use any dilations, so they're all congruent, which means that this side over here is also A, and this side over here is also B, and this over here is C. And I could just keep going around the triangle like that, or the square, I should say. All right. So now I have everything labeled, and what do I notice? Is there any equation that I could draw, that I could write, having to do with this thing that I've just created? Well, I might consider how I would find the area of what I called the outer square. So let me just remind you again, this is the outer square over here. Now, how might we find the area of this square, which is the space inside of the square? There's more than one way to do it. One way that we could do it is we could just take the side length of the square. All the side lengths are the same, and then we would square the side length. Okay, it's called, which means we multiply it with itself, right? So, for example, if I had a rectangle, and let's say that this was 3, and let's say that this was 7, and I wanted to find the area of the rectangle, then I would just do 3 times 7, right? Now over here I have a square, which is just a rectangle where all the side lengths are the same, and each side length has a length of A plus B. Okay, the side length is not just A, and it's not just B, it's A plus B. So if I add the length from here to here with the length from here to here, then that gives me the length all the way from here to here. So each side length has a length of A plus B, which means if I wanted to find the area of this square, then I would do A plus B times A plus B. And another way of writing that is A plus B squared. Okay, it's not a coincidence that it's called squared when we do that, because that is how we would find the area of a square that has this as a side length. We would put an exponent of 2 over it, we would multiply it with itself. Okay, so this right over here tells me the area of the outer square. Okay, now, is there another way that I could find the area of the outer square? Well, there is. What I could do is I could figure out the area of this inner square over here. So if you imagine me shading this in, I don't want to shade it in right now because then I would cover all these C's that I have over here. But I could find the area of this inner square, and I could combine that with the areas of these 4 triangles that I have around here. So if I find the area of this plus the area of these 4 triangles, that will also give me the area of this big square over here. Okay, so another way of doing that is to find the area of this plus the area of all of these. Okay, so what is the area of this inner square right over here? Well, each side length has a length of C. So that means that the area of this square is just C to the 2nd power, C squared. Okay, so I'll write over here, area of the inner square is C squared. Okay, and put an equal sign in here. And now what about the areas of all of these triangles over here? Well, how do we find the area of a triangle? The area of a triangle is, to find the area of a triangle, we multiply the length times the base, or the base times the height. It's maybe easier to see it from this one here. We could call this the base, and we could call this the height, and then we divide it by 2. So the area of each triangle is equal to A times B divided by 2. That's how we find the area of a triangle, okay? But we have 4 triangles over here. And so the area of, let's use a different color. The area of all 4 triangles would be 4 times this. It's just this plus this plus this plus this, right? I hope I said that 4 times. Or in other words, this times 4. So this gives me the area of all 4 of these triangles put together. But you know what I could do here? I have 4 times A times B divided by 2. We could simplify that a little bit. And since 4 divided by 2 is just 2, we can rewrite this expression as simply 2AB. This over here is not the area of just 2 of the triangles. This is still the area of all 4 triangles. It's exactly equivalent to this, it's just written in a different way, okay? Now, again, if I wanted to find the area of the big square, we already have one way of doing that over here. We could do that another way. Area of the outer square by combining the area of the inner square with the area of these 4 triangles. So we could say that the area of the outer square is equal to c squared, that gives us the area of the inner square, plus the area of these 4 triangles over here, which is 2AB. Okay? Now, what is the relationship between this expression and this expression? Well, this expression represents the area of the outer square. But wait a minute, this expression also represents the area of the outer square. And therefore, these 2 expressions must be equal to each other. So what we're going to do now is we're going to just write the expressions again, those same expressions that I just drew pink rectangles around, except we're going to put an equal sign in between them, because since they represent the same thing, they must be the same. They must be equal to each other. So we can, based on this picture that we drew over here, we can write a plus b squared must be equal to c squared plus 2ab. Okay, now what we're going to do is we're going to expand this over here. So you know what I'm going to do? I'm going to do that on the side in a different color. What haven't I used yet? Let's try, well, I think I did use green already, but whatever. Okay, so I'm going to expand this. What does this mean, a plus b to the second power? That literally means a plus b times a plus b. Okay, so I need to distribute over here. So what I have here is I just need to make every combination of what's in here with every combination of what's in here. So the first thing that I have is a times a, which is a squared. Next, I have a times b, which I'll just write as ab. So now I have a plus ab. Next, I have b times a. So I can write that as plus ba. Plus, and then the last one, last combination to make is b times b, which is b squared. Oh, I was doing so well. Okay, and I didn't do anything with this, so I'm just going to keep this the way it was. Now, can I simplify this at all? Yes, I can. Here I have AB, A times B, and here I have B times A. Remember, these really just stand for numbers. So I know that A times B is the same thing as B times A. No matter what 2 numbers I have, if I call one A and I call one B, if I multiply, if I have the A first, and like 3 times 4 is the same as 4 times 3, right? Okay. So these things are really the same, and I have 2 of them, which means I can write this thing as 2, let me keep this one the same, a squared, and then ab plus another ab, even though it's written ba, I can think of it as being written ab because it means the same thing. So ab plus ab is 2ab. Okay, and then let me just copy this b squared over here. So notice that I have a plus 2ab on the left side of this equation, and I have a plus 2ab on the right side of this equation. And what I can do now is I can subtract 2ab from both sides. Okay, remember, anything that you do to one, you can do anything that you want to an equation, as long as however you change one side of the equation, you have to change the other side in exactly the same way. So if I want to subtract 2ab from this side, I would also have to subtract 2ab from this side. Okay? But since I had to begin with plus 2ab on both sides, then on both sides, this is just going to cancel out, and I have left over on the left side a squared plus b squared, and I have left over on the right side c squared. Oh, look at that. We have the Pythagorean theorem. A squared plus b squared is equal to c squared. So if we have a construction like this, which is made up of 4 congruent right triangles, then we know that the relationship between the legs and the hypotenuse of those right triangles must be a squared plus b squared equals c squared. And since we can make this construction using any right triangle, it didn't have to look exactly like the right triangle I had to begin with. It could have looked like this, it could have looked like this. As long as it's got a right angle in it, then we'll be able to make a similar sort of construction like this. So that means that the relationship between the legs and the hypotenuse of any right triangle is this right here, which is called the Pythagorean theorem. Okay, so that's it, and have a great day.